Alright, welcome back. Math 1910, Calc 1, Chapter 4, Section 2, learning how to calculate area. This is going to lead into our definite integral here soon, but we have to understand a little bit how to do Riemann sums. Okay, so we're going to use sigma notation, and we're going to write and evaluate sums. You should be able to do this in your calculator as well. Alright, and we want to be able to use that and find the area of a plane region. Alright, using limits. Okay, so some of you guys have seen this, some of you guys haven't. Alright, sigma notation, this is the giant summation. Alright, it's a capital sigma. Alright, and it means that we're going to do some sort of summing. So we read this in terms of the sum from I equals 1 to n of ai, where ai is our function that's being evaluated at all of our different increments of I. Okay, so this is really where we're going. So the giant Greek letter, sigma, all right, denotes that we are going to do some sort of summing. All right, if we follow the definition here, I is the index of summation. Okay, AI is the ith term, right? That's the function that we're putting the values of I into. And then we have upper and lower bounds. All right, so we're going to get into, how we apply that here shortly. So if we look at how sigma notation works out, if we have the first one here, A, right? We have I, we're going to sum I equals 1 to 6 of I. So that means we're going to do I, we're going to do it for every value from 1 to 6. And we're going to sum them. So it really ends up being when I is 1 plus I2, or not I2, but when I is 2, when I is 3, when I is 4, when I is 5, and when I is 6. So when we write this out as a summation, we're substituting in the values of I into the actual function I there. So we're going to get 1 plus 2 plus 3 plus 4 plus 5 plus 6 when we get that entire sum out. Okay, so I believe that gives us 21 there if we do that. Alright, if we look at the next one, we're going to start it when I is 0. So we're going to sum from when I is 0 to when I is 5, and we're going to substitute it into I plus 1. So we're going to have to do 0 plus 1, 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, and 5 plus 1. Okay, which equates to 1 plus 2 plus 3 plus 4 plus 5 plus 6. Okay, which also ends up giving us a value of 21. Okay, let's look at the next one. We don't have to use the letter I. We can use whatever letter we want. For us, we're probably going to use N a lot of times, potentially K. All right, but let's take a look at C here. C is we're going to evaluate J from 3 to 7 of J squared. So that means we have to go 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared to get our value. Okay, and then in D, it doesn't always have to be a numerical value. We can sum it using a, just a value of 1 to n that, handles all the scenarios. So we're going to do K equals 1 to n of K squared plus 1. So we're going to get 1 over n times 1 squared plus 1 plus 1 over n times 2 squared plus 1 plus dot 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 means we're going to continue all the way up to the nth term. So 1 divided by n of n squared plus 1. Okay, and then, lastly, probably the most important one that we're going to use a lot in here is I equals 1 to n of f of xi times delta I. So those are going to be our change in x, okay? So we're going to have, substitute in from 1 to n, so f of x1 delta x plus f of x2 delta x. Notice that delta x isn't getting the 2, only the I term is, okay? So we're going to be evaluating different parts when we do sum notation, okay, or summation notation, or sigma notation. However you kind of want to see that. Most commonly it's probably called sigma notation, but we're going to be doing, sums. We're going to use this later on too, because we're going to get into Riemann sums and things like that here shortly, so you're going to understand. Now there's some basic properties with this. So we have, different properties for addition and multiplication. Addition and subtraction, then multiplication of a constant. So the first one's the distribution property using multiplication. So if we have the sum of I equals 1 to n of ki, we can factor out that constant of k, because it's just a constant. It's not going to affect what's being substituted in, and it's a multiple at the end. So sometimes it's important for us. just like when we pulled the constant out in front of the integrand in the last section. All right, and then when we have the summation, we can write it as two separate sums. So if we have AI plus or minus BI, remember both of the A and B functions have to be in terms of the I for us to evaluate. So it's just kind of like having a composite function when we have like an f of x or a g of x type scenario here. And we can do each summation separate, all right, and then get our final answer at the end. So make sure you write these guys down, all right? So we have theorem 4.2, and there are 4. These are very important. We're going to come back to theorem 4.2 when we're going to do substitution. Substitution. I can't speak today. Substitution. Okay, so what we're going to do is we're going to simplify some of our summations down so they're in terms of I, and then we're going to replace them. All right, so anytime we have a constant, it's just going to become Cn. Anytime we have the sum from I equals 1 to n of I, we're going to replace it with n plus 1 divided by 2 times n. Okay, anytime we have the summation from I equals 1 to n of I squared, we're going to replace that and do some simplification as n times the quantity of n plus 1 times the quantity of 2n plus 1, all divided by 6. Okay, and then anytime we get the notation I equals 1 to n of any I cubed, we're going to get n squared times the quantity of n plus 1 squared divided by 4. This is very, very important that you have these 4 written down because you won't be able to simplify if you can't reference these. Alright, so make sure that you have these down, and then as we go through how to use them, have these at your wayside, because we're going to get sums in terms of c, I squared, I, and I cubed, and we're going to replace them with their n equivalents that are shown here for our summation formulas. Okay, so let's take a look. And why would we do that? Well, let's take a look at this problem here. Okay, it's got a combination of i's and n's, and we want to do it for when n equals 10, n equals 100, n equals 1,000, and n equals 10,000. All right, so we're going to evaluate this sum, but it's hard to do because we have i's and n's and things like that. So we can apply theorem 4.2. So we're going to factor out the 1 over n squared, and we're going to be left with the term I plus 1. We're still going to have the sigma in here, okay, but we're going to factor out 1 over n squared. And then we're going to rewrite that, okay, as two separate summations. So it's going to be 1 over n squared, okay, and then that's all going to be multiplied. We're going to have the sum from I equals 1 to n of I plus the sum of I equals 1 to n of 1. And then we're going to use our theorem 4.2 right here, and we're going to replace those i's with n's. Okay? So, when we rewrite as two separate sums, I'm going to replace I equals 1 to n of I, okay, with what I have from theorem 4.1, which is n times n plus 1 divided by 2. And then I'm going to replace the summation from I equals 1 to n of 1, or 1 to n of 1, with n. Those are both on theorem 4.2, so I'm going to step back a slide here. So we are using number 2 and number 1 here. We're replacing the I with n times n plus 1 divided by 2, and we're replacing our constant, which is 1, with 1n. Okay, so very important that we do some replacing here when we do this. Then we can simplify some things and go from there. Alright, so as we do that, I'll step back a slide here. Okay, we can distribute the n through on the top, so you're going to get n squared plus n divided by 2. Okay, and then we can distribute the 1 over n squared, alright, through. So different ways that we can simplify this down. So when you finish all the algebra, we end up getting 1 over n squared times the quantity of n squared plus 3n divided by 2. Okay, and then we can factor an n out of the numerator. When we do that, we're left with n plus 3. Okay, and that n in the numerator will cancel with one of the n's in the denominator, and we'll end up with n squared plus 3, or I'm sorry, just n plus 3 divided by 2n when we do that. Now, it's easier for us to substitute in our values. And we're going to evaluate it at 10, 100, 1,000, and 10,000. Now I expect you guys to be able to do the substitution on your own. We're going to replace all the n's with 10, 100, 1,000, and 10,000, all right, to get our values. Okay, So how do we use this? Well, we're going to use this to calculate the area. Okay, in Euclidean geometry, okay, the simplest thing for us is a plane region or a rectangle or a square, those sort of things. Okay, because we often look at it and we say, oh, okay, the formula for that is base times height. Okay, so that's the definition of the area of a rectangle. So we can do that, all right, to find the area under a curve. So very, very important. When we start taking other plane regions, we can start doing this with the area under the curve and doing an area approximation using rectangles by drawing multiple rectangles underneath things. Okay, so just kind of how we develop, the area of a triangle. It's 1/2 base times height. Well, where does that go? Because the triangle technically is going to be, 1/2 of our rectangle. Okay, and we're a square for the most part. So that's where we develop the area of a triangle from. Okay, but then once we know different areas, we can find different areas of polygons and hexagons and things like this. And this is all basic geometry that we've learned in the past. Okay, you did a lot of things like that, multiple repetition. But for us, we're going to do this by conics, different graphs. Okay, that we're going to have that's going to eliminate certain elements where we might have some approximation above a curve or some approximation below a curve that we're going to have to cancel out and find the best method to do this. Okay, so if we take a look at some different examples here, okay, if we want to find the area of a circular region, right, we can do that by approximating using a bunch of triangles. And some of those triangles are smaller than the circle, and some of those triangles are larger than the circle. So in one approximation, we're going to get an area that's slightly larger than the circle. In another approximation, we're going to get an area that's slightly less than the circle. But look what happens. We're evaluating the same circle, but what are we doing here? If we change the number of times we increment n. So if we look in the first example, if we only increment n 6 times, okay, we won't be, as precise. But if we increment n, 12 times, we're going to be a lot more precise, and we're going to eliminate a lot of that error, all right, from going over or not, going under and not having enough. All right, so if we take about, look at this, for each value of n, we have an inscribed polygon is less than the area of the circle, okay, and the area of the circumscribed polygon is greater than the area of the circle. So, as we're changing that value of n, okay, we're getting closer and closer to the actual value of the circle. Okay, so for us, we're going to do it with conics. We're going to do it with different graphs of different curves. So in this example, okay, we're going to find or approximate the area of a region, okay, of a specific graph. In this case, we're going to take a look at the graph of f of x equals negative x squared plus 5. Okay, and we're going to find the area that it covers between x equals 0 and x equals 2. There's going to be two methods that we're going to use to do this. We're going to call it, the left hand and the right hand. If we take a look at that, and we're going to get into this a little bit, but if we notice the figure on the left, what's happening? We're approximating the area of rectangles underneath the curve. So what we're going to add up those rectangles, we're going to get the area that's in blue. Okay, notice that there's some pinkish color there, where there's the top of the rectangle to the curve. Okay, that's where our error is because we're not accounting for that area. So our area will be less than the curve in this scenario, all right, but it'll be kind of close. And then if we cut it down and make a bunch more rectangles, in this example, I'm asking you to do it with 5 rectangles. If we did it with 10 rectangles, we would get more exact because we would have more rectangles and we would eliminate more of the pink area that's under the curve. Okay, if we look at the example on the right, when we do our rectangles, we're going to say that our rectangles are greater than the curve. So we're going to have an error that's larger than the area under the curve when we do this approximation. Okay, but once again, if we take a larger number of rectangles, the amount of error that we're going to have will decrease. Okay, so we're going to find the area of the region, okay, of f of x equals negative x squared plus 5, and we're going to find that between 0 and 2. We're going to use a left hand and a right hand method as we go through this. But I want you to see that some of the error or some of the approximation is going to lie below the circle or the curve, and some of the approximation is going to lie above the curve. So either way, we're going to have a little bit of error, but we eliminate the error by taking more rectangles when we do the calculation. All right, so let's do this one. We have the right endpoints of the 5 intervals. Okay, they're going to be 2 over 5. Now, how do we get that? Let's step back. All right, we're going from 0 to 2. So we're going to do y2, or x2, sorry, minus x1 divided by n. Okay, so 2 minus 0 divided by 5, because that's how many rectangles we want. Okay, so our boundaries divided by how many rectangles we're going to do. So that's where the 2 over 5 come from. Okay, and then we're going to do that for i's, the right endpoints. So in this case, if we look at the right endpoints, we're looking at the curve on the left-hand side. Okay, these are the right endpoints. We're looking at the 2/5, 4/5, 6/5, 8/5, and 10/5 that are going underneath the curve. Okay, so this is from the left-hand side here when we do this. So they're the 5 right endpoints, though, if that makes sense. So notice, why are we calling it endpoint? Because that's where the top of the rectangle touches the curve. All right, if we look at the top of each one of these rectangles, that's where it's going to, touch the curve. And we're going to do this for I equals 1, 2, 3, 4, and 5, because we wanted to do it for 5 rectangles. Okay, and that's going to represent our specific values that we're going to evaluate. Because if we notice, from 0 to 2/5 is 2/5, from 2/5 to 4/5 is 2/5, from 4/5 to 6/5 is 2/5, 6/5 to 8/5 is 2/5, and 8/5 to 10/5 is 2/5. Why are we doing that? Because that's the width of each triangle at the bottom. Okay, if we look at each triangle from 0 to 2/5, from 2/5 to 4/5, from 6/5 to 8/5, so on and so forth. Okay, that's how wide that triangle is that we're looking at. And then we're going to multiply that by the height, because we're going to do a sum. We're really just taking, the area of each triangle and adding them, or rectangle, the area of each rectangle and adding them up. So we've calculated our endpoints. Okay, and we're going to evaluate at each endpoint. So we're going to evaluate at 2/5, 4/5, 6/5, 8/5, 10/5, so that we can get the height of each rectangle. I'm going to step back to the slide again. The height of each rectangle at that point. Okay, so when we write this out, we're going to get the summation from I equals 1 to 5, because we're making 5 rectangles, and then we're going to do f of 2i over 5, okay, because each width is 2/5, okay, and we want to find at each 2/5, high, what is the height of each one of those rectangles. Okay, so we're going to evaluate each one of those points. So when we do this, we're going to get I equals 1 to 5, okay, and then we're going to get f of, this is where we're substituting in the 2i over 5 into the original equation. So I'm going to step back a couple slides here. The original equation is f of x equals negative x squared plus 5. So we're going to substitute in our 2i over 5 quantity squared. We're going to replace x with 2i over 5. Okay, and then we're going to multiply them all by 2/5 at the end. So if you put this in your calculator, you should roughly get 6.48. Or if you have to do it by hand, okay, you're going to have to do negative 2 times 1 divided by 5 squared plus 5. Okay, and then we can multiply by that 2/5 at the end to everything. And then you'd have to do when I is 2, so you'd have negative. And then you'd have 2 times 2 divided by 5 squared plus 5. Then when I is 3, you'd have 2 times 3 divided by 5 quantity squared, and make sure it's negative in front, plus 5. And then you'd have negative 2 times 4 divided by 5 squared plus 5. And then you would have, the last one, negative 2 times 5 divided by 5 quantity squared plus 5. And then all that gets multiplied by the 2/5 at the end. So make sure that you're doing this right in your calculator and you're getting approximately 6.48 as you do that. So what does that 6.48 represent? That's the area under the curve. All right, from 0 to 2, I'm going to step back. We're looking at the figure 4.8. We're looking at A here. We just calculated the area under the curve using the rectangle approximations. So from 0 to 2, okay, the area under the curve of negative x squared plus 5. We just calculated that area there, okay? So if we want to do the left endpoints, we just did the right endpoints. Now we're going to do the left endpoints. So let's step back to this slide here. So we're going to do the picture on the right. We're going to do the left endpoints. So notice the left endpoints of the rectangle. So with these rectangles, we're going to be approximating the area that's slightly above the curve. We're going to include all of the curve and then have the area above the curve there. And we're going to use the left endpoints, and we're going to evaluate 0 now. We're going to evaluate 0, 2/5, 4/5, 6/5, and 8/5. Okay, those will be the heights of the rectangles that we're going to evaluate, and that's where they're touching the curve. Remember, we always want to evaluate where the rectangles are touching the curve. All right, so let's move forward here. Now, so the left endpoints, okay, are going to be 2/5 divided by I minus 1, okay, because everything's shifting and we're using left endpoints now. So we're going to evaluate when I equals 1, 2, 3, 4, and 5 now when we do this. Okay, so we're going to substitute into our sub. Now, okay, we're going to substitute in 2I minus 2 divided by 5, okay, because we distributed our 2/5 to our left endpoints. And then we know that the width of each rectangle is still 2/5 when we do this. Okay? So now we just literally plug the sum into our calculator and get our value. So we have 8.08. So that makes sense, right? Our previous one was 6 point something. This one's 8 point something because it's greater than the curve. So there's that small error between the two. Okay? So we can take a look and say we know that the area of the region is somewhere between 6.48 because those are the rectangles underneath the curve, and somewhere less than 8.08 because those are the rectangles that are a little bit greater than the curve, and we know the area of the actual region has to lie between those two curves. Okay, we're going to find out later on how to do this a little bit easier using some calculus. As far as how we use our integrals, but we're going to do that in the next section here. Okay, so if we want to take this, we're going to talk about upper and lower sums. That's kind of essentially what we just did, right? Upper sums, we did the rectangles that were above the curve, and lower sums, we just did the rectangles that were below the curve, okay, when we do this. So even if we have a curve here from A to B, all right, of the function f, we're going to find the region under the curve. So what do we really need to do? Again, this is what we did in the first example. We do b minus a. In our first example, b was 2, a was 0, so we did 2 minus 0, and then we divided by n, which was the number of rectangles we're using. So same way that we set this up here, okay? So our subintervals are delta x, so we're going to use a little bit different notation here. It's no different than how we found the I piece in the last example, all right? B minus a divided by n. So, the limits of our area that we want to go through on the curve divided by the number of intervals or the number of rectangles that we want to take when we do this. Okay, so if we look at how the endpoints are going to work out, all right, it'll look like that, and we'll evaluate each one. Okay, and then we're going to take a look at the difference. If we have f of the lowercase mi, that's the minimum value of the subinterval, and f of the capital Mi, okay, that's the maximum value of the subinterval. Okay, so that's doing below and above. It's like what we just did with the last example. So if we have the inscribed rectangle, so that's the rectangles laying inside the curve, okay, and then we have the circumscribed rectangles, the rectangles that are outside of the curve or above the curve. So we're going to have to find the area of the inscribed rectangles, so the area, the rectangles below the curve, and we're going to have to find the area of the circumscribed rectangles, the rectangles that are greater than the curve when we do this. So how do we calculate this? We do the lower sum, which is represented with a lowercase s of n, equals I equals 1 to n. Okay, so the sum from I equals 1 to n of f of little mi times delta x. Okay, and then the upper sum is going to be capital S of n from I equals 1 to n of f of capital Mi times delta x when we do this. Okay, so we have to understand the lower sum, that's the rectangles under the curve. The upper sum, that's the rectangles that go above the curve. And the curve is whatever function we're talking about, right? In the first example, the curve was f of x equals minus x squared plus 2. So that's what I'm talking about when we talk about the curve of the region, okay? So, if we base this into the example that we're talking about here, the lowercase s of n, okay, those are the ones that are below the rectangle, okay, versus the larger rectangles, the ones that are above the curve. So hopefully you can see between these two pictures, all right, that we're using the area, inscribed rectangles, the ones below the curve, and the circumscribed rectangles, the ones above the curve. So we're going to have, slightly, but we're going to use that and we're going to define the region of where the area should be. Eventually we're going to find out how to find the actual area, but we're going to do approximations now. So let's do an example here. We want to find the upper and lower sums for the region bounded by the graph of f of x squared equals x squared and the x-axis between x equals 0 and x equals 2. All right, so that's going to help us. We have our curve, all right, and we have our boundaries that we're going to do. So we have to partition the interval into n subintervals, right? Because it didn't say, hey, we're going to do this 10 times or we're going to do this 5 times. We're going to just do this for all intervals, so we're going to use n subintervals in this case. So it's going to be important because we're going to incorporate theorem 4.2 later on here too, okay? Just stepping back to something towards the beginning of the lecture. All right, so if we're going to begin, we're going to partition this, all right? So our delta x becomes b minus a, so it's going to be 2 divided by, or 2 minus 0, and we're going to divide by n. If I would have said do it by, 5 different rectangles or something, it would have been, n would have been 5, and it would have been 2 over 5 like the first example. So just so you kind of know that. All right, we're going to do it for n subintervals though. So that's our delta x, okay? And we're going to do the different endpoints, okay? So we're going to do the left endpoints and then the right endpoints to do this. So we're going to do the inscribed rectangles, okay? And then we're going to do the circumscribed rectangles, okay? So we have to make sure that we know what we're doing. So if we do the left endpoints, okay, we're going to do 0 plus I minus 1 times 2 over n. Okay, we're doing 0 because we're starting at 0. If we were starting somewhere else, this would be shifted over a little bit. So just know that we define our left endpoints as 2 times I minus 1 divided by n. Okay, now if our interval, say, went from like 2 to 4, okay, instead of having 0 there, we would have a 2. Okay, and we would be going to 4. So just so you know, that's how that one's going to play out. And we would not have 2 over n, we would have like 4 over n. So you got to take this into account here. So it's really important that you understand how to write lowercase mi and uppercase mi. That 0 represents where we're starting from. Okay, so when we do the left endpoints, we're going to get 2 times I minus 1 over n. And when we do the right endpoints, when we simplify down, we're going to get 2i divided by n. Okay? So the I minus 1 is how we handle left endpoints. The the I times the is what we're just going to do with the right endpoints. Okay? The 2 over n, right, that's what we had to calculate from here. That's where the 2 over n is coming from. Okay? And the 0 is coming from, we're starting at 0. Okay? So we have the I minus 1 and the I. Okay, those are coming from just our general rule that we did before. Okay? And then we'll step back forward. All right, so we want to use the left endpoints, okay, and we're going to calculate this. So we're going to do the lower sum. So it's going to be I equals 1 to n of f of 2i minus 1 divided by n times 2 over n. So we're going to take that 2i minus 1 over n, and we're going to substitute that into the original function, which is x squared. Okay, the 2 over n is our delta x. Okay, then we simplify a few things down before we do that. Okay, so when we put that in, remember it's squared because we're putting into x squared, right? F of x is x squared. So we're substituting in that 2 times I minus 1 over n into the x squared because that's the function. And then the 2 over n is our delta x. Okay, so we've calculated all that. We've calculated our delta x, our left endpoint, our right endpoints, and now we're substituting into our function. Okay. Now notice that we have something in terms of I and we have something in terms of N. Okay, we're going to have to do some simplification here. I'm going to step back one slide. If we square everything out and multiply through by 2 over N, okay, you're going to get this. We're going to get N, or I equals 1 to N of 8 over N cubed times the polynomial of I squared minus 2I plus 1. Now, how do we do this in terms of N? This goes back into theorem 4.2. We have to replace I squared, and we have to place I in terms of N, and we will replace the 1 in terms of N. Okay, so that comes back to theorem 4.2, so you can pull that up as we go through this. The 8 over N cubed, okay, it's just a constant that's in front. We're going to pull that out of the sum, okay? So when we do that, we're going to have 3 different summations. The sum from I equals 1 to N of I squared minus 2 times the sum of I equals 1 to N of I plus the sum from I equals 1 to N of 1. And then we go back to theorem 4.2 and we replace the I squared, the I, and the 1 with its N equivalents. So that's where those came from. So go back to theorem 4.2 and see how we replace the sums in terms of N when we do this. Okay? So you'll be able to see that. That's literally all we did. Now it's just algebra from here. We're going to simplify down everything as much as we possibly can. We might have to, distribute some things, do some FOIL, all those different things. So when we simplify down using algebra, I'm not showing all the steps here, okay? We should be able to get these functions here, okay? Remember, this was just for the lower sum. So when we do all the algebra simplification, you should get 8/3 minus 4 over N plus 4 over 3N squared. So that's the lower sum. If we do the upper sum, okay, the upper sum, now we're going to evaluate from 1 to N, I equals 1 to N of f of 2I over N times 2 over N. So 2 over N is still our delta x, and then 2I over N, right? Those are going to be endpoints of the rectangle. That's what we're going to substitute in when we do this into our equation. Remember, our equation is x squared. Okay, so we're going to replace it. This is exactly how we did the left endpoints, but the right endpoints are a little easier because there's not as much math because the distribution of the I piece isn't as large. So we're going to replace x with 2I over N. Okay, so we're going to have 2I over N squared times delta x, which is 2 over N. I equals 1 to N. Same thing here. We're going to multiply through, simplify as much as we can. So we end up with this summation, I equals 1 to N of 8 divided by N cubed times I squared. And you guessed it, we're going to pull out that 8 over N cubed and be left with the sum of 1 to N of I squared. And then we're going to replace the I squared, all right, with theorem 4.2. So whatever I squared's equivalent was, which was N times N plus 1 times 2N plus 1 divided by 6. Then we simplify all this down algebraically, and when we do, we get the upper sum to be 8/3 plus 4 over N plus 4 over 3N squared. So that's our upper sum when we do this. A lot of math involved here. We had to find the upper sum and the lower sum. Okay? Now, another way we can do this is use limits at infinity. So we can take the limit as n approaches infinity of s of n, okay, and we can write this down as the limit as n approaches infinity of I equals 1 to n of f of little mi delta x, and it also equals the limit as n approaches infinity of I equals 1 to n of f of capital Mi, right? Remember, the lower m and the capital M mean the upper and lower sums. Okay, so when we want to use this and apply this, f has to be continuous, it has to be non-negative, it has to be on an interval, closed interval from a to b, all right? And we have to say that the limits have to be equal to each other. That is, right, as n approaches infinity, the lower and upper sums exist, and they are equal to each other. So that's the whole point with this sum. Okay, so delta x has to be b minus a over n. I already went through how to calculate that. And f of mi and f of capital Mi are the minimum and maximum values on the subinterval. Okay? So if we do this right, we can obtain the same limit for the upper and lower sum. So we can take a look at the squeeze theorem, right? Because remember, the squeeze theorem is where we have two graphs that have the same limit and we're shoving a third one between those two, right? So it also has to have the same limit. So we can use the squeeze theorem for that process here. So we can kind of define the area of this function as the limit as n approaches infinity, all right, from the sum of I equals 1 to n of f of ci times delta x. And we just have to calculate our delta x. That hasn't changed, right? It's b minus a over n. All right, that's the width of each sub-interval as we go through this. Okay, so we want to find the area of the graph of f of x equals x cubed between the x-axis and x equals 0 and x equals 1, okay, that we have shown in the figure here. All right, sorry I had to pause the video for a second and move that down so you can actually see it. All right, so I'm going to reread this to you. It says, find the area of the region bounded by the graph of f of x equals x cubed, the x-axis and the vertical lines x equals 0 and x equals 1. Okay, so it's shown here below. All right, we have the graph of f of x equals x cubed. Obviously, we're not showing the entire graph. We're only showing the portion of the graph from 0 to 1. Okay, so what we're going to do is do our approximation. So it's very important. The x equals 0, x equals 1, those are our boundaries. Okay, and the x-axis. So later on, this will make more sense when we get into integrals and doing that sort of thing with it. All right, so we have to see that, f is continuous on the interval 0 to 1. We're going to partition the interval from 0 to 1 into n subintervals. Once again, we're using n because it's not given saying that, you're going to make this into, 5 rectangles or 10 rectangles or things like this. So each width, our delta x is going to be 1 over n. Remember, how do we get that? It's going to be 1 minus 0 divided by n. Okay, and the 1 and the 0 are a and b. They're the endpoints on the interval. Okay, so that's where our delta x comes in. Okay, so we can choose any value in the ith subinterval. So using that definition, so we can use the right endpoints. I would always choose the right endpoints. They're easier. You could choose the left endpoints. It really doesn't matter if you want to. But the right endpoints are always easier. Remember, those are I over n. And remember, we're starting at 0. That will change if we're using starting at a different value here, okay? But we'll use ci equals I over n. They're the most convenient ones. So when we calculate this area, we're going to say the limit as n approaches infinity of I equals 1 to n of f of ci times delta x. So our ci in this case is I over n. Our delta x is also going to be 1 over n. And remember, our f of x equation is x cubed. Okay, so we're going to substitute in our ci's, which is I over n, into the x cubed portion. All right, so if we take a look at this, the limit as n approaches infinity of I equals 1 to n. Okay, again, it was x cubed. We're replacing x with I over n. Those are our ci's, so it'll be I over n cubed times 1 over n. That 1 over n can go in front right now. Okay, and then we're going to have I cubed over n cubed. That other n cubed can come out, and we just really have the sum from I equals 1 to n of I cubed. And then we can go back to theorem 4.2, okay, and get our replacement n values. Remember that 1 over n to the 4th, I'm going to step back a slide here, is because we have 1 over n cubed that we pulled out in front, and then we're multiplying by 1 over n. So 1 over n cubed times 1 over n is our n to the 4th. Okay, so that's where that's coming from. So we're going to take the limit as n approaches infinity of 1 over n to the 4th times the sum of I equals 1 to n of I cubed. Using theorem 4.2, we're replacing I cubed, the sum from I equals 1 to n of I cubed, with n squared times n plus 1 quantity squared divided by 4. Okay, so we're going to take this limit now as n approaches infinity. So what we need to really do is make sure that we multiply through on the numerator. This is where you have to remember your limits as n approaches infinity from section 3.5 that we went to. Okay, remember there was 3 rules. If the exponent on the numerator was greater than the denominator, then if the exponent in the numerator was the same as the exponent in the numerator, I can't speak, I'm sorry. The exponent on the numerator was the same as the exponent on the denominator, or the exponent on the numerator was less than the exponent on the denominator. So if you need to review section 3.5, go back and do it. But those were the three scenarios that we did as the limit as n approached infinity. All right, so let's multiply the top out here. So you're going to FOIL the n plus 1. Okay, when you do that, and you're going to get n squared plus 2n, okay, plus 1, and then you're going to distribute the n squared through. Okay, once everything is all said and done, this simplifies down algebraically into the limit as n approaches infinity of 1/4 plus 1 over 2n plus 1 over 4n squared. Now we know the limit of 1 over n, or 1 over 2n as n approaches infinity is going to go to 0. And we know the limit as n approaches infinity of 1 over 4n squared is going to go to 0. Alright, so essentially the only thing that's left is the 1/4. Okay, so that's the final solution. So the area under the curve from 0 to 1 of x cubed ends up being 1/4. Alright, well that's it for this lecture. So hopefully we did a lot with sums and understanding how to approximate the area under the curve using rectangles, or we could use it, for whatever type of intervals we want and be able to choose, a left hand and a right hand endpoints, whichever one was more convenient for our problem. So I'll work through more problems in depth on the board as well. This should be good to get you guys started and going here. So else, if you have any questions, feel free to email me. Let me know if you need a Zoom meet or team meet or anything else like that. Else, guys, have a great day. I will see you in class.